Hi, welcome back to Mrs. O'Graham's Maths. We are carrying on with doing the worked solution videos for the D&D resource book. I've put a link to their webpage in the video description, and you can order their resources online. They have fantastic books for practices for the externals, and I highly recommend ordering the paper copy to have a go like it's a real paper. Is a little bit better for maths than trying to do it digitally. So a big thank you to them for allowing me to share their resources in this way so that I can help you go through worked solutions. Today we're looking at complex numbers, so it's standard 91577, and we're on the practice external assessment number 3 from the D&D book. Okay, cracking on with question 1. So we're going to go ahead and solve this quadratic. Now, just before I do that, because it's an achieved question only, you can put this into equation solver and solve it if you have an updated version of the graphics calculator. Now, I say updated because we need it in SURD form. Now, this particular model won't do it for me, so I'm going to have to go through and show you the by hand method anyway. But if you do have an updated calculator, you can use that just to go straight to equation solver. You do it under here in the equation solver menu and solve that quadratic. If I try to do it on this one, it's going to give me a decimal answer here where I need surds. So for my calculator, I have to do it by hand. But if you do have a newer calculator, then just use that for the achieved questions. Okay, now if we're solving using the quadratic formula, we've got z is equal to minus b, so that's minus 4, plus or minus the square root of b squared minus 4 times AC, well A is 4 and C is 11, all over 2 times A. So let's work out some of those things. We've got 16, oh, that should have been a minus just there, minus 16 times 11, that's going to be the square root of minus 160. So we've got minus 4 plus or minus the square root of negative 160 all over 8. Now, negative, or the square root of 160, we can turn that into, we could take out a factor of 4 there. So that would be 4 times, if we do that, let's see, 4 times 40. Actually, I can go one better. We can take out a factor of 16 from that. It'd be 16 times 10, because we always want to look for the highest square number that we can do. So this will be equal to the square root of 16, which is 4, times by root 10. So back over to what we were doing over here, this is going to be minus 4 over 8 is minus a half, plus or minus the square root, 4 times the square root of minus 10, all over 8. Well, the 4 over 8 is going to cancel to a half. So root of, let's put that half at the front like this, because we're going to do it, we're trying to get it into this order here. And then the minus root 10 is going to be root 10 times by I. Now we're taking a little side quest to do part B on an updated question. So this is a new question in the latest edition of the book, so that's why this bit of the video looks a little bit different, but we're going to go ahead and work out v to the 6 over u in polar form. Okay, so let's start with thinking about what v to the 6 is. Okay, so that will be 2 cis pi by 8 to the 6. When we're in polar form, that means we do 2 to the 6 cis of pi by 8 times by 6. So 2 to the power of 6 is 64, and an eighth times by 6 is 6 over 8, which is 3/4. So this will be cis of 3 pi by 4. So then v to the 6 over u is 64 cis of 3 pi by 4 over 8 cis of pi by 2. Now division, we do 64 over 8, and we do a subtraction of the arguments. So 3 pi by 4 minus pi by 2. So 64 over 8 is 8, and 3/4 take away a half is 1/4, so this will be pi by 4. Okay, let's prove that this thing is purely imaginary. So it means that we're going to rationalize the denominator and hopefully come up with something that only has i's attached to it. So let's start with p plus pi over q minus qi. To rationalize the denominator, we will times by the conjugate of the denominator. So we need q plus qi. Okay, now multiplying across the top, we have pq plus PQI plus PQI plus what do we have next? PQI squared all over Q squared minus Q squared I squared. Okay, now this PQI squared, the I squared turns to minus 1. So we have PQ plus PQI plus PQI plus, well, actually, let's put that as 2PQI minus PQ. So those two cancel, and we're still over Q squared. Now we've got a plus Q squared because that bottom I squared turns into minus 1. We end up with 2PQI over 2Q squared. So that is entirely imaginary. We can simplify it a bit further. We can cancel the 2's. We can cancel one of the q's. So that is P over QI. So therefore, imaginary only. Okay, finding these solutions for z cubed means we are using de Moivre's theorem. Now it's already in polar form, so that's helpful. So our first solution, we will do the cubed root of m, which is m to the third, and the argument gets divided by 3. So 1/4, if you need to check it, you can just pop it on the calculator. 1/4 divided by 3 is 1/12, so it's pi by 12. Now, the solutions are symmetrical around the Argand diagram. So here's our first solution. Our next one, we're going to have these spaced evenly around the circle. And a full circle is 2 pi. So if we wanted to divide that up into 3 pieces, we would do 2/3 of pi. 2 for the whole circle, and then divide that by 3. So the next solution around would be somewhere over here, where we've added on 2 pi by 3 to make it adding on 1/3 of a circle. So our second solution, the modulus hasn't changed, the length away from the origin, only the angle has. So we'll do pi by 12 plus 2 pi by 3. Okay, so 1/12 plus 2/3 makes 3/4. So we have m to the 1/3 cis. Let's fix that up. That should have been a third. I think I wrote a half just before, so I fixed it now. It's m to the third cis, and then it's 3 pi by 4, so 3/4 of pi. So we're kind of like that much. All right, so this gap here is where we've added on 2 pi by 3. Now we need to do that again one more time to get our final one, which will be another 2 pi by 3 around. So m to the third again, cis of 3 pi by 4 plus another 2 pi by 3. So 3/4 plus 2/3 makes 17/12. So m to the 1/3 cis of 17 pi by 12. Now once we've gone over the pi line, we actually want to come back at it from a negative direction. So 2 is a full circle, so do 2 minus the 17/12 that we just had, we got minus 7/12. So it's minus 7 pi by 12. Okay, we need the Cartesian equation of this locus. And we always start these sorts of ones by saying that z is equal to x plus iy, and then we can sub in. So we have on the left, we've got x plus iy plus 7 plus 3i. And then 3 times the modulus of x plus iy minus 1 minus I. Now modulus means we're going to take the real parts and square them. We're going to take the imaginary part, so this is y plus 3, and square them, and then do the square root of it, like this. On this side, we've got the real part is x minus 1, and the imaginary part is y minus 1. Again, we're just looking for the coefficients of I. We don't include the I itself. Now, if we square both sides, so that we can carry on solving this, we'll have x plus 7 squared plus y plus 3 squared equals 9. Don't forget to square the 3 as well, times x minus 1 squared and y minus 1 squared. Both of those would be times by the 9. And just keeping in mind what we're aiming for, we're aiming for this form of that. So we'll just see what we can collect up and sort out. So next step, let's expand the brackets. We've got x squared plus 14x plus 49, y squared plus 6y plus 9 is equal to 9x squared. Let's do this in 2 stages actually, minus 2x plus 1 plus 9 times y squared minus 2y plus 1. Okay, so then if we multiply these through, we've got 9x squared, 18, 9, 9y squared, 18, 9. Okay. Now let's bring all of the x's and y's to the left and all the constants to the right, just looking at the format that we're aiming for. Okay, so we have on the left, if we do x squared minus 9 squared, we have minus 8x squared. We've got 14x plus 18. So 14 plus 18, as we bring that over, is 32. We have the y squared minus 9 squared is going to be minus 8y squared. And then we have a 6y plus 18, so 6 plus 18 is 24. Okay, now constants, we've got 9 plus 9 on the right. So we have 18 on the right, then we're going to take a 9 over and subtract that, and then we'll subtract the 49 off of it as well, and we've got minus 40. I'm going to rewrite this in with the negatives reversed, because I think that's going to be easier to work with. Okay, the first thing we can do is divide by 8. So we've got x squared minus 4x plus y squared minus 3y is equal to 5. We need to do completing the square on the x parts and the y parts. So we've got x minus 2 all squared. Just have a think what that would give us. It would give us x squared minus 4x plus 4, which is almost what we want, but we've got an extra 4, so we take off that extra 4. And then same with the y minus half of that 3 is going to be 1.5 squared. If we were to expand this, it would give us y squared minus 3y plus 1.5 squared, which is 2.25. So we need to take off that because that's more than what we wanted. We only wanted the y squared minus 3y part. So take off 2.25, that equals 5. Now, last step is to take the constants all over to the right. Okay, so 5, add on the 2.25 and add on the 4, and we've got 11.25. Now, if you needed to describe what that was, this is now a circle where the center is at x equals 2 and y equals 1.5, and the radius is the square root of 11.25. We didn't need that for this particular answer, we just needed to put it into that form, but I think it's helpful for you to know what that answer means. Okay, so let's expand this one for question 2a. Again, if you have an updated calculator, you can put this all into the calculator, so long as it can display surds for you. My one can't, so we will need to do the expansion fully here anyway. So let's start by expanding the brackets. We've got 3 times 5 is 15. 3 times minus 3 is minus 3 root 3. Sorry, the 3 times the minus root 3. Then we have these 2 times together makes 10 root 3. And finally, these two gives me a negative 2, and then a root 3 times root 3 is root 3 squared. So it's 2 times 3. In other words, it's 6. Okay, if I multiply... Oh, no, let's tidy that up first. So this is equal to root 3. 15 minus 6 is 9. 10 minus 3, so 10 root 3 minus 3 root 3 is going to be 7 root 3. So we have 9 root 3 plus 7 root 3 times root 3. The root 3's will times by itself will be 3, so that gives me a 21. And if we're going to be pedantic about it, it would be 21 plus 9 root 3, just so it's in that order there. For b, we need to expand this bracket here. So we'll do 2a minus 2i plus ai minus I squared is equal to 11 plus bi. The minus I squared becomes a plus 1 because I squared is minus 1. So then that will cancel out. Now let's look at the real parts of this. The real parts are 2a plus 1 on the left and 11 on the right. So a is going to be 5. The imaginary parts, on the left we have minus 2i plus ai is equal to, on the right hand side, that's got to equal bi. Well, a we just worked out was 5. Divide through by the i's, we've got minus 2 plus 5 is equal to b. So b is equal to 3. Okay, for C, you can go about this 2 ways. You can know the geometry of what this means, or you can set z equals x plus iy and then get an equation out of it. I like these questions. I think about them geometrically, so that's what I'm going to do with this one. So for I, think about this as being the modulus minus 2 minus I. Once you've set it to be z take away something like this, that's something, when we're inside of the modulus, that's like the starting point. So if we go 2 and then minus I, it's here. Now the rest of the instructions tell us that the length, so modulus is length, the length that we have of z away from that 2 minus I point is equal to 3. So this becomes the center of a circle. Z can be any distance away from that, anywhere away from that, so long as the distance it is 3. So it's going to go up to 3 here, out 3 there, and it's not a great circle I'm drawing. Hold on. So let me just pop the corners, or sorry, the outer parts that are easy to get there. It's not corners because it's going to be a circle. Now I need a circle that joins the dots. So all of the points that are 3 away from that center of 2 minus I. And then for part 2, the maximum value for the real portion of z, well, here's our real axis. We want to know how far up the real axis can this go. Well, our limit is just here for how wide that circle can go in that direction. So that is 5. Okay, rearranging this one, we've got root 3x is equal to 2x minus 2, just by bringing this up and multiplying it. Let's square both sides and we can get rid of the root 3 there. So then we'll have 3x squared is equal to 2x minus 2 squared. That's the same as doing 2x minus 2 times 2x minus 2. Sometimes it's easier to see it that way around so we don't miss any terms. So now we'll have 4x squared minus 8x plus 4. If we bring the 3x squared over to the right-hand side and subtract, we'll end up with an x squared minus 8x plus 4 is equal to 0. There's a clue in the question that the solution is going to be in this form, so it's not going to factorize easily. Let's pop it in the quadratic formula. So minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So 8 over 2 is 4 plus or minus. Okay, we've got 64 minus 16 is 48. So I would have the square root of 48 over 2. Now, if I take out, I'm trying to take out a factor of 48 that's a square number. I think 16, yes, 16 works. And try and take out the biggest one that you can. So we have 4 plus or minus. Now, if I take, let's just pop this over to one side. So 48 would be equal to the square root of 16 times 3. So the square root of 16 is 4, and then we leave that as root 3. So over here we'll have 4 root 3 over 2. Well, 4 over 2 cancels, so it's just 2 root 3, like this. One final step. The answer was looking for it to be only the x, only the one that has the plus in it here. So our final solution is to say x is 4 plus 2 root 3. Okay, for E, okay, so first of all, let's start by working out u over v. So we have 3 plus ai over 2 minus ai. We want to be able to find the argument, so let's start by rationalizing the denominator so we can get this in a more normal looking format. So times it by 2 plus ai over 2 plus ai. Multiplying that across, we will have a 6 plus 3ai plus 2ai plus a squared I squared. And then 4 minus a squared I squared. Okay, so the I squared turns into minus 1, so we have 6 minus a squared as the real part plus 5ai all over, again on the bottom the I squared becomes minus 1, so this is 4 plus a squared. Now the real part of that 6 minus a squared over 4 plus a squared, and the imaginary part of that is 5a over 4 plus a squared I. Now we're told that the argument is equal to pi by 4. On an Argand diagram, then that looks like this. We have an argument of pi by 4. It creates an isosceles triangle because pi by 4 is 45 degrees. So this side will be equal to this side. The real part will be equal to the imaginary part. So let's use that on the equation that we've just got. So real is equal to imaginary. So we have 6 minus a squared over 4 plus a squared will be equal to 5a over 4 plus a squared, which means that 6a squared is equal to, 6 minus a squared equals 5a. So a squared plus 5a minus 6 equals 0. For that, I think we can factorize here. So we would have minus 1 and a plus 6 will work. So a equals 1 or a equals minus 6. Then considering where it needs to be on the Argand diagram, it's got to be in the positive quadrant where both the real and imaginary parts are positive. So consider what happens if we put 1 as a positive number into here. That's going to stay positive. If we put 1 into here, this stays positive. But if we put minus 6 in as a, this one will end up being a that one, the real part's fine, but the imaginary part will be 5 times minus 6 is minus 30 over a positive, so that's going to become a negative. So our a minus 6 solution doesn't fit this particular one, so we can identify that a has to be equal to 1. For this question here, we have a nice little use of the factor and remainder theorem. So if these two have the same remainder when we put when it's divided by x minus 3, it means we can put 3 in as the value of x, and it will come to the same answer. So if we do that for this one, it'll be equal to if we were to do it for this one. So if we work that through, we've got 27 plus 9k minus 3k equals 3 cubed is going to be 27 times 2, gives me a 54, minus 9 plus 4k. So on the left here, the k's, that's 6k, and then if we take off the 4k there, we have 2k. And if we do 54 minus 9 and then take off the 27, we've got that's equal to 18, so k equals 9. Part B, we want to show v over w on the Argand diagram, so let's work that out. We've got 3 minus 5i over 2i. I'm going to use the calculator for this. It's only an achieved question, so we can just pop that straight in. And that comes to minus 2.5 minus 1.5i. So on the Argand diagram, we're going to minus 2.5 there, and down 1.5 is just here. So that is u over v. Okay, for part C, if 1 plus ki is a solution, it means that we can put it into our equation and it will be true. So let's do that. 1 plus ki here plus 34 is equal to 0. Okay, so 1 plus ki is going to give me one, all squared is going to give me 1 plus 2ki plus k squared I squared. K squared I squared is going to become minus k squared. Now if I times everything through by 2, I've got 2 plus 4ki minus 2k squared minus k squared I plus 34 is equal to 0. Now if we're thinking in complex terms, it's actually equal to 0 plus 0i. So we can compare the real and imaginary parts there. Let's go with the real. That's probably the most ordinary way to think about this. So 2 minus 2k squared minus k plus 34 equals 0. So that's just picking out all of the real parts of this, like so. Which makes me think that perhaps the imaginary might be a quicker route. So the imaginary parts, I've got, let's use a different colour. Here we go. So minus k squared there and a 4ki. So on the imaginary, I can go with 4ki minus k squared I is equal to 0. So k, take out the, it's equal to 0i. So take out the i's. I'm just dealing with the coefficients. Take out a factor of k, and we've got k and 4 minus k. So k equals 0, or k equals 4. The final step is to always check if the solutions that we've got are valid, if they actually work, especially when we're dealing with squares of things. Sometimes extra things could be introduced that don't work in the original equation. So if I was to set k is equal to 0, so if k equals 0, then 1 would be a solution. So 1 would be a solution, because I would have 0 in as k just there. Now if I do 2 times 1 squared, actually let's pop that down here. So I'd have 2 times 1 squared minus k times z, which is 0, plus 34 is equal to 0. Well, that clearly is not true. So k cannot be equal to 0. Now check if k equals 4, then 1 plus 4i is a solution. Now if we pop that in to our calculator, let's put that in as 1 plus 4i, like so, and then let's put it into the equation. 2 times that answer squared minus k is 4, so it would be 4 times the 1 plus 4i plus 34, and you can see that comes to 0. So 1 plus 4i works, therefore k equals 4. For part D, we've got another one where the question has changed, so this is just a little update to the original video. We've got a complex number w that looks like this, and we want to find the possible values of p, because we've got a p in there, that would make the modulus of w equal to 3 root 2. Now, we've got a division in w, but we can use the fact that if you're doing the modulus of a over b, that's equal to the modulus of a over the modulus of b. Okay, so for the modulus of w, it will be the modulus of p plus 3i divided by the modulus of 1 minus 2i. Now if we're working out modulus, we do the square root of the real part squared plus the imaginary coefficient squared, not the I, just the 3. And we're going to do that on the bottom as well, the real part squared plus the coefficient of the imaginary part squared. And we're setting that equal to 3 root 2. So the next line, we've got p squared plus 9 over the square root of, well, 1 squared is 1, 2 squared is 4, so we've got root 5 is equal to 3 root 2. So if I multiply the right-hand side by the root 5, I will get p squared plus 9 is equal to 3 root 2 times root 5. Now with surds, we can turn that into 3 root 10. We can combine those two surds there. Then if we square both sides, we've got p squared plus 9 is equal to the square of this, so don't forget to square the 3 to make it a 9 as well. Well, let me just get that back. So we will have 9 times 10, which is 90. So p squared is equal to 90, take off that 9 will be 81. So p is equal to plus or minus 9. Okay, the last one on this paper is about types of solutions. We want only one real solution to this equation, so we're going to rearrange it into a quadratic and then look for the discriminant. So if we cross multiply here, we've got kx plus k is equal to 2 root 2x minus k. Multiply that k through there, we've got kx plus k squared. Let's square both sides. So we'd have kx plus k squared is equal to 4 times 2x minus k. So we have k squared x squared plus 2k cubed x plus k to the 4 will be equal to 8x minus 4k. Bringing everything over to the left-hand side, we've got k squared x squared, 2k cubed x minus 8x plus k to the 4 minus 4k, that's a plus 4k, sorry, is equal to 0. Now, we actually have a quadratic there. We've got an x squared term. We've got x terms in the middle, and we have a constant at the end. So the a part of that quadratic is the k squared, the b is 2k cubed minus 8, and the c is k to the 4 plus 4k. For there to be just one solution, we want the discriminant to be equal to 0. So we take the b part, square it, and minus 4 times the a part times the c part, and set that to be equal to 0. Right, if we square this thing, we will have 4k to the 6 minus 32k cubed plus 64. Then expand this next bracket, we've got minus 4k to the 6 minus 16k cubed is equal to 0. The k to the 6's cancel out. We've got negative 32 minus 16. So we have 64 minus 48 k cubed equals 0. So k cubed will be 64 over 48, which is 4/3. So k will be the cubed root of 4/3. Which is 1.1006 or 1.1. Okay, that's that paper completed. And hopefully you found that useful. If that was helpful to you, please do like and subscribe because it helps other people to find it too. And go check out the other solutions that I have for the D&D workbooks. Bye-bye.